using computational fluid dynamics. So with that being said, John, I will let you take it over, and we look forward to your presentation.
Okay, thank you very much, Thad. Good morning, everyone. The title of my presentation is Using CFD to Aid in the Design of a New Sea Lock at Ijmuiden. So in the Netherlands, recently, a new sea lock was put into service. In fact, it's almost exactly 1 month ago. And this sea lock is referred to as the sea lock at Ijmuiden, which we'll hear more of today. And it's my understanding that the sea lock is currently the largest in the world. So at Arcadis, I manage a small group that does CFD analysis for a living, essentially. And with this project, we played a small role in analyzing how the leveling system for the lock would work. So what I'd like to do today is briefly introduce you to the project, explain what the role of CFD modeling was in the work that was carried out, share with you some of the results of that work, and then make a final comment about the lock today. Afterwards, certainly I'd be interested in answering any questions that I could for you. So before moving on, I would turn your attention to the image on this slide. It is an artist's rendering of the sea lock. And one of the things that makes this lock unique, besides its size, is the design of the doorways. So the doors for the lock are designed to slide back and forth rather than to rotate. And within those doors is housed the leveling system itself. And as I mentioned before, it was the design of the leveling system that we were asked to analyze and work with team members to help design. So to give you a little background about the project, almost 100 years ago, there was a lock referred to as the North Lock. And I won't attempt to pronounce the name of the lock properly, but the North Lock was located at Ijmuiden, and it was decided that it should be replaced because the materials from which it was built were now obsolete, but perhaps more importantly, the size of the lock was limiting the size of the vessels that could pass through it and ultimately end up at the Port of Amsterdam. So with that as background, a new lock was envisioned to be built adjacent to the Old North Lock. And what we see in the photograph is an aerial view of, we'll call it the lock complex. And kind of in the center of the figure is the old lock at Ijmuiden. And the new one was built adjacent to it, which visually would be to the left of the lock in the center of the frame. And currently, both the old and the new lock are in service with the intention of closing the old lock down at some point. The project is located on North Sea in Ijmuiden, and this is a Michelin roadmap. And if you look at the upper left part of the figure, you'll see the words Ijmuiden, and it's really beneath the letters IDE that the lock complex is located. And so the lock complex serves what's referred to as the North Sea Canal, and that's the canal that would take Ijmuiden to the Port of Amsterdam. As I mentioned before, the new sea lock is currently the world's largest, and it is 500 meters long, 70 meters wide, and 18 meters deep. And so what this figure is intended to show is a comparison of the new lock's size compared with 4 of the existing locks in the complex, those being the small lock, the south lock, the middle lock, and the north lock. As I mentioned before, my understanding is that currently all of the locks are in operation with the intention of closing the north lock down once, well, in a few months after some experience is gained working with the new lock, which is the largest one in the center of the figure. The focus of my presentation will eventually move to the design of these locked doors. And so again, and one of the things that makes the project unique is the fact that the doors are designed to slide in and out of pockets um, on the side of the lock and contained within the doors piece of rigging. The largest photograph that we're looking at shows one of the C-lock doors in place, and at the lower left part of the figure you can see at least part of the pocket opening where the door would be withdrawn into when it was opened. The image at the upper right is a CAD drawing of one of the doors, and the thing that I would point your attention to would be the 16 little windows that you see near the bottom of the door. And those windows have bars in front of them, and those are in fact the openings through which water would go through the doorway when the gates are open. And I should comment and say that the doors are symmetric in design, and so on the side of the door you can't see in the figure, it would visually look to be the same. Braking bars positioned at the openings, and then again the sluice gates themselves that control the flow of water and the leveling of the lock are located in the center of the doorway. And then the figure or photograph at the lower right shows one of the doors being put into place. The doors are 72 meters long, 11 meters wide, and 25 meters in height. They were manufactured in South Korea and then brought by boat to the construction site. The Dutch Ministry of Infrastructure and Environment awarded the project to something referred to as the Openij Consortium. And so this was a group of 3 businesses, BAM-PGGm, VolkerWessels and DIF. And these 3 firms were responsible for designing, building, and financing the project. And they're also responsible for maintaining it for the next 26 years. In addition to those firms, there were a number of other companies that were involved with the consortium and the work also, one of them being Arcadis. In the work that we carried out, we collaborated most closely with Royal Haskoning and VolkerWessels. And so with respect to the project was started in 2015. At that point, design studies were carried out that were aimed toward developing a preliminary and eventually a final design for the lock itself. Construction was started in the summer of 2016. 4 years later, in the summer of 2020, the first lock was put in place, and then just a month ago on the 26th of January, the C-lock was open for operation. I would note that the choice of leveling system and that would be to bring waters through the doorways, was chosen in the tender phase of the project, so very early on, and by agreement of the project partners, before the construction could start, it had to be proved that this option would meet the requirements of the Environment Ministry. And so it was really in this early phase of the project that we were involved with CFD analysis, which very shortly I'll get on to talking about. Before I move on, though, this is a photograph of the finished lock shortly after it was opened. And so you can see in the foreground one of the sliding gates, and you could also see, or at least make out, the pocket within which the gate could be drawn into, and then adjacent to it is a second bay, and there's a spare gate that's also located on site. So 3 gates were constructed, ultimately 2 in use, and then 1 serving as a spare. So the lock leveling system for this project is contained within the sliding doorways that are located at either end of the lock. And in designing a leveling system of this type, there are a few considerations that need to be made. One certainly is wanting to gain an understanding of how the gates should be actuated. In other words, there's 16 gates in each door, what number of gates should be opened at what rate, and as those gates are opened, how does that affect the filling and draining time of the lock? In addition to that, when the lock is filled or drained, the flow of water in the lock will affect the mooring systems that may be required for vessels that are located in the lock. And so with this particular project, Deltaris, which was a partner that we worked with as well, carried out one-dimensional flow calculations using a program called LockFill. And the equations that make up this computer program are fairly easily understood. One of them being an equation that relates the discharge of water Q through, in this case, the locked door. And this will be the only equation that appears in the presentation, so I promise you. So if you look at the center of the slide, you'll see the equation Q equals mu A square root 2G delta H. And so all this is saying is that the discharge of water through the gate will be equal to a coefficient of discharge times the flow area afforded to the water going through the leveling system, multiplied by the square root of 2G, and delta H being the head difference across the doors. The tricky part here is that the discharge coefficient is unknown a priori, and its value changes as the percent opening of the gate opening changes. And so in this particular project, one of the roles of CFD analysis was to help determine what these discharge coefficients should be, since they will depend on the specific design of the gate or the leveling system. So the CFD work that my group carried out was first and foremost aimed at estimating discharge coefficients so that the lock filling and optimization simulations could be carried out accurately. And then, in addition to that, the CFD analysis was used to assess flow patterns that wouldn't be resolved in a one-dimensional calculation. And then, more importantly, to carry out 2 additional smaller analyses. One, to answer questions about the design, specific design questions of the sluice gate, how it should be shaped, how the braking bars should be designed, and then to answer questions about vibrations that could develop within the door as a result of the flow through it. So in total, we kind of had or in summary, we had a hand-holding exercise between really the 3D calculations and the 1D work that's traditionally done. And in parallel with this, a 1:40 scale physical model of the facility was also constructed. And at the end of the day, verification tests were done with the physical model to support the results of the numerical work. And the idea behind this combined approach was to essentially shrink the project schedule so that this leveling system could be proved and not delay the construction of the project. Also to increase the reliability of the design by using these different methods, and ultimately to reduce some of the costs associated with the design of the leveling system. If all the work, for example, was done in a physical model testing lab, the costs would have been higher than they were with this combined approach. And then also, as we shall see, within the leveling system itself is quite a complicated array of support structures and other features which are difficult to incorporate into a physical model, but a little more easy to incorporate into a 3D numeric model. So just kind of to summarize the purpose or the role of the CFD modeling here was first and foremost to determine these discharge coefficients so that we could design the leveling system and determine how it should be operated, and then also to carry out some optimizations to improve the design prior to construction. The CFD modeling procedure consisted of really 4 steps. The first steps was a validation of the modeling approach. We used a commercial program in our work known as Flow3D, and that's sold here and developed here in the US by a company called Flow Science. That particular program was not familiar to other members of the project team, and so at the outset of our work, what we wanted to do was prove that it could produce results which were accurate and usable for the project. Having done that, kind of the 3 basic tasks that we were given were to first calculate discharge coefficients based on the preliminary design of the leveling system. Deltaris then used the results of this work to progress the lock-fill simulations and better understand how the system should be operated. In parallel with that, we carried out design optimizations based on recommendations from the construction firms and other engineers on the projects. And then finally, to wrap things up, based on the final design that was chosen for the gate, we carried out final design calculations. The figures on this slide don't exactly look like a lock gate, and they shouldn't. They're from the validation test case that was chosen. Speaking to the photograph on the top, what we did was to analyze or to simulate a laboratory experiment where a jet was issued from a wall into a quiescent body of water. And this negatively buoyant jet, as you see in the photograph, as it moves away from the wall, which would be on the left-hand side of the figure, it disperses, and at various locations downstream, the experimenters had measured velocity profiles. The reason that this test case was chosen was that some of the other work that was done really was meant to address what kind of currents in the lock would set up when the leveling system was operated. So an important aspect of answering those questions is being able to understand how the jet flows being issued by the exits from the leveling system would evolve inside the lock. At the image in the lower image is a result from one of the CFD calculations, and what you see in it are 4 vertical bars in bold, and those are locations where some of the experimental data was taken, and those were cross sections where we compared the results of the numerical work with the experimental results. So referring to this somewhat busy figure, what we see are the results of the experiment, and superimposed on top of them are the results of 3 CFD calculations. And so as we move from the left to the right, we're at increasing distances away from where the jet was issued, and with the red dots we have experimental data. So those would be velocities that were measured, and then superimposed in green, yellow, and blue are the results of comparable numerical calculations. And so the good news is that everything looks like it's on top of each other, at least pretty much. And further good news is this, that the green dots represent the results of calculations used or provided by simulations carried out with a program known as STAR CCM. That is another commercial CFD software package that people use. And you'll see that the results that were produced with those simulations with that program, which the project team was familiar with, look very similar to those that were produced with the Flow3D program. In fact, there's strengths and weaknesses to the results that are provided by either program, but in general, the agreement with the experiment's quite good. One thing that we learned from this work is first that we should expect a certain amount of reliability from the numerical calculations that will be carried out. And second, we learn also how to set the calculations up in terms of mesh refinement and resolution it's necessary to carry the work out properly, and how, in this case, turbulent effects should be simulated as well. So it's a nice test case that set us up to finally get to the work that we wanted to carry out, and that was to understand how flow moves through the proposed leveling system for these gates. What we see in the image on the right at the top is a cutaway through the locked door, and what you see are 1, 2, 3, 4 complete tubes or bays through which the flow moves. So starting on the surface that's closest to us, you'll see 3 vertical bars that are located in the openings, and those are referred to as braking bars, and they have 2 purposes. As flow goes into the doorway, the braking bars prevent large debris from being dragged in with the flow as well. And as flow would exit the door, essentially going the opposite direction, those bars help break up the jet flow to minimize the disturbance caused on the downstream side of the doorway. So when the lock's being filled, for example, it would help disrupt currents that would have or make the mooring system requirements a little bit more. Couple things to point out. I had mentioned it before. The doors are designed to be symmetrical. The lift gates are in the center, so there's an arrow in the top figure, the middle arrow pointing to where the lift gates are. Those are sluice gates that are moved up and down to control the flow of water through the doors, and then they're braking bars, as I said, at both sides. Also, as I had mentioned before, it's a fairly complex structure. The ballast chambers are for the doors are located obviously within the doors. There's maintenance shaft, control equipment, and the leveling system itself is housed there. In the lower figure, you see kind of a vertical slice cut through one of the doors. And as you move from the left to the right in the image, you'll see near the bottom of that cutaway 16 openings. And those would be the openings through which the water goes, and the sluice gates that control the flows are located at different positions. So on the left, 4 of the openings are completely open, and then as we move to the right in various degrees, the sluice gates are being dropped. So it was quite an interesting piece of engineering overall. Our particular assignment involved primarily understanding how the flow moves through the doors themselves. And at the outset of the project, we didn't know, and it was uncertain, how much of the domain that we were really interested in or would have to model in order to gain a fair understanding of what was happening within the doorways. So initially, there were simulations carried out. What is referred to here as the full domain. So the simulations included the lock, as we see in the figure on the left. They included one of the doorways, and then within the doorways, the model setup included all the detail associated with the 16 tubes that would carry flow through the doors. So in the 2 images to the right, you see all the detail that necessarily was included in the initial calculations. Now, another piece of good news was this, that as we progressed through this study, it became clear early on that the flow through each of the tubes was about the same, and that the flow through one tube was not affected by its neighbors. And so, to put it more succinctly, what that meant was that we didn't have to necessarily worry about modeling flows through the entire lock and all the doors and really create kind of a monster analysis, but instead we could focus on the flow through an individual tube and then easily extrapolate the results to the full setup. Once that was recognized, the focus of the work then shifted towards an analysis that just focused on the flow through one of the openings. And so what we see on this slide is an image where you can see different openings or tubes through the door. At either end of each opening are the yellow braking bars. And then in our analysis, what we've essentially done is to select one of those openings, and then through the opening and surrounding it, we've created or defined the model domain, which is essentially the area within which we're doing these calculations. And so you can see this kind of light blue box that surrounds one of the openings, and that represents and illustrates what the model domain looked like in the preliminary calculations that we carried out. I guess just a couple things to point out. The simulations were carried out for one opening only, and in order to simulate the flows entering and exiting the tube properly, it's necessary to move the boundaries away from those openings a certain distance. And so on the upstream side, the upstream boundary where flow would enter the computed area, that was 7.5 meters upstream from the face of the door. And on the downstream side, it was about double that. And actually what we learned, and as we'll see later, is when we carried out the final calculations, really not to have the boundaries disturb the solution in the area of interest. It's necessary, at least for this problem, to move those boundaries even further away. And then the other thing I would just point out would be that the simulations that we carried out were for 4 different gate openings, one at 5% open, 15%, 40%, and 100%. And let's see if I can make my presentation move forward. There we go. So the first calculations were carried out with the gate almost closed or 5% open, and I won't spend a lot of time on this slide or the next one, but what I do want to do is just point at the fact that for the 2 conditions we'll look at, this 5% open condition and 100% open condition on the next slide, the calculated discharge coefficients vary significantly. So the point to drive home is that, well, these important values that we need, they don't just vary by a little bit, so we could maybe ignore the variation. They're significantly different by a factor of 2. So this type of analysis is really quite valuable and needs to be done for this work. The images on this slide are from the results of the CFD calculation for the 5% open case. The mesh resolution or the size of the control volumes in the calculations varied significantly, at least in the vicinity of the gate. You need to be using control volumes that are about 1 to 2 centimeters in size in order to get results which are grid independent. Speaking to the images from the CFD calculation, all of the images are colored by flow speed. The units for the flow speed are meters per second, and then the color bars tell us something about what the flow speeds are. So starting with the figure at the upper left, that's showing the flow beneath the gate in a 5% open condition, flow speeds that are greater than 6 meters per second are colored red, and in fact the maximum flow speed beneath the gates about, in these calculations, about 8 meters per second. The image on the bottom shows a plan view cut at a horizontal plane just above the floor of the opening, and so you can see how the flow accelerates significantly as it goes underneath the gate, and then the image on the upper right is showing a side view through the gate for this condition. As I mentioned before, what I wanted to do was contrast the discharge coefficient calculated for this case, which was 0.76, with the one that's calculated for a 100% open case. When the gate's fully open, the discharge coefficient, the way that they're calculated, is equal to 0.41, so about half the value. And that just gives you a sense of, over the range of gate positions, if we're interested in understanding how the leveling system will work and making use of that information, the determination of these discharge coefficients is really quite important. As I mentioned before, this initial work was provided back to the engineers at Deltaris, who then used the information to develop initial control algorithms for the gates. And based on input that we received from other members of the construction and engineering team. We then used essentially the same setups to address a couple issues related to the detail flow patterns through the gates. The first issue that we dealt with was with respect to the design of the braking bars. And so, as I had mentioned before, one of their functions was to break up the high-speed jets or the high-speed flow that would be issued from each of the 16 openings in each of the doors. The initial design of the braking bars was one where the cross-section of the bars was square or rectangular, and the bars were flush with the face of the doors. One thing that was noted in the initial calculations was that the distribution of flow through the openings between the bars was not even, and that created not concerns, but something that would be nice to get rid of for the incoming flows. And then on the exiting flows, there were fairly pronounced disturbances in the flow patterns leaving the openings, and those disturbances persisted a good distance into the lock. So what we did was to look at a couple variations of the braking bar design, moving the braking bars to the outside face of the doors, moving them closer together, which is referred to as case 1 here, making them triangular in cross-section, which is referred to as case 2, and reducing the size of the bars, which is referred to as case 3. So the image on this slide requires some explanation, and I'll try to give it. What it's showing in plan view is the calculated variation of flow as it moves from the left to the right past the braking bars. So I'll try to explain how to interpret the figure now. On the horizontal axis, we have position in the up and downstream direction, and in the vertical axis, we kind of have lateral position across one of the openings through the door. As I mentioned before, the flow is going from the left to the right, and at different transects, which are identified as the green vertical bars, we've outputted each one of those locations a velocity profile. So starting with the upstream-most profile, which would be located at the left-hand side of the figure, you see that the velocity distribution across the channel is about the same for cases 1, 2, and 3. And that's something that we would expect, that the upstream effect of the braking bars should be negligible or minimal. And then as we approach the bars, those profiles remain about the same. On the downstream side of the bars, and that would be at X locations greater than 6, at the first 3 transects, we see quite a bit of disturbance, or at least a variation in flow speed as we move across the area where we've plotted the results. And that should be expected. There's a great deal of turbulence that's created, and as we move in the downstream direction, the amount of that variation begins to go away. But one thing we see when we get to distances beyond about 8 meters away from the opening is that the results for case 2, so those would be the dashed results, the velocity profile starts to look a lot more regular compared to the results for case 1 and 3. And so what this indeed is showing us is that these triangular braking bars seem to work better in that they smooth the exiting flow from the door. And between the preliminary design for this and the final, the triangular braking bars were adopted just for this reason. An additional thing to point out is that from the preliminary design or to the one where the braking bars cross-section was changed, it has a minimal effect on the discharge coefficient. So it doesn't incur more head loss or significantly less head loss. And it does smooth the velocity profile on the downstream side of the doorways compared to the preliminary design. So on this figure is a image on the left that shows kind of the configuration of the braking bars. So if the flow was entering the doorway, it would be coming from the side of the image where the dimensions are, and it would be coming kind of towards you from the upper right to the lower left part of the figure. And then the figures to the right show calculated velocity patterns. Obviously, not all the vectors are shown, but they show the flow going from the left to the right through one of the doorways, and they show the orientation of what we'll call the new braking bars. So they're triangular in shape, and then they're positioned not within the tubes, but on the face of the doorway. The other thing that we needed to or wanted to address before the design was finalized were concerns related to vibration. And the idea here was that some of the mechanisms that are used to control the sluice gate opening and closing can be affected by vibrations. And we wanted to gain some level of assurance that the frequency of the turbulence, or the main frequencies associated with the turbulent flow through the leveling system, the frequencies there would be quite different than the natural frequency of the system used to actuate the gates. So there are a couple things to point out from a computational point of view. This starts to be a pretty heavy lift. To answer the question properly, the simulations are carried out in 3 dimensions, kind of as usual, but also done in a fully transient way, so that what we're doing is computing time series of velocities and pressures, and then we're using those time series to carry out spectral analysis to figure out what the predominant frequencies of the turbulence are. Speaking to the figures on the right first, and the top one, that's probably the most simplest one to look at. This would be from a simulation where the braking bars were still square in their original position, and the flow is moving from the left to the right. The field is colored by speed, so when the flow accelerates and gains speed, it goes from a cooler color to a hotter one, to the red. And what you see as the flow moves from the left through the first set of braking bars is the development of vortices, if we were to look at vectors as well. So you're developing kind of vortices that are being shed alternately as the flow passes the braking bars. As we move to the right in a continued fashion, those vortices start to go away. And what I've marked on the figure as a red dot, so that would be just left of the X location minus 1.4 in the center of the channel, we had various sampling points set up in the numerical experiment where the time series data was output. In the lower figure, we're looking at the same data, except that rather than showing velocities or velocity magnitude, we're plotting vorticity, or kind of the rotation in the flow, still outputting the results at the same location. And then using this information, if we now look at the figure at the lower left, we can calculate spectra, our power spectrum, that tells us at what frequencies are these disturbances most predominant. So we see, to the left of the figure, disturbances at a lower frequency, and then the frequency gets a bit higher. We have another peak, and then what's not shown is the good news, and that is that what we were wanting to avoid were frequencies, if my memory serves me correctly, that are kind of on the order of 50 or 60 hertz. So, you know, these disturbances were well away from where we wanted to be. So that box was checked, so to speak. Once the preliminary work was done, as I mentioned before, on the basis of lessons learned through our work and the work of others, the gate design was finalized. What you see in the figure that shows the final gate design, in its final design, it looks a little bit more like a plunger, kind of a thin wall, and then at the bottom of it, we have kind of the kind of closure gasket or mechanism that'll come down at the bottom of the gate opening. And then also the braking bar design had been updated as well. As I mentioned before, at least for the computer people, we also learned that, you know, much to our chagrin, the up and downstream boundaries for our calculations should probably be moved a little bit more. So at the end of the day, with these changes all made to the analysis, final design calcs were carried out, and I guess the thing that I would mention, which is probably the thing that most modelers mention at this point, the simulation times are starting to get quite large because they're being carried out in 3 dimensions over periods of time in a transient way. And as I've marked on one of the figures, the boundaries had to be moved quite far away. So in the case of the 5% open case shown here, you know, you have a very small opening below the gate, yet your model domain, because of a lot of specific features of this problem, is actually located 30 meters upstream where flow enters, and then 100 meters downstream from where it exits the modeled area. So that was something that's normal to numeric calculations, but here it was a bit more normal than we expected. The flow patterns in general, you know, are about the same with the design changes made. For the 100% open case, there are a couple things to kind of point out. One thing that wasn't expected was that the jet flow showed in these simulations on the downstream side of the gate openings, the jet flow showed actually kind of attaching to the water surface, or not going down and attaching to the bottom. That's something that was studied with the physical model and is also, you know, relevant to mooring design as well. The other thing is that if we move our attention to kind of this figure on the right in the center, there are little supporting fins that come in from the wall inside each of the individual tubes through the door. And there was questions asked about whether or not it made sense to essentially seal those up, you know, put a little wall in it so it's a smooth tube. The results of these calculations showed that, you know, they create a separation zone, but really in terms of discharge coefficient and their hydraulic effect are minimal. So it didn't make sense to recommend that those regions be closed off. And the other thing that these simulations showed collectively was that the braking bar design was doing at least a better job than the preliminary design of breaking up the jet flows exiting the leveling system. Just to give you a sense of some of the results, that initially with the preliminary design for each of the 4 opening conditions we looked at, we have discharge coefficients there in the center column of 0.76, 0.73, 0.68, and 0.41. With the updated design, the discharge coefficients really didn't change much. And for that reason, the 2 middling cases were not computed, and instead we essentially scaled the results of those discharge coefficients and used them in subsequent lock fill calculations. One thing that supported that decision also was finally, at the end of the day, the results of scale model testing as well. So on this particular slide, we see photographs of the scale model that had been constructed, and in the table on the lower left, we see some of the computed results compared with what was measured in the lab. And so one of the nice things was that as the design evolved, major performance changes for the leveling system because that would result from changes in the discharge coefficient, they just didn't appear to be there. And then the results also, agreed that were computed, agreed well with what was measured in the laboratory as well. So this gave a good feeling of confidence about the ultimate system that was chosen. And then now that construction has been completed, kind of referring back to a month ago today, I think that I lifted this text from the city of Amsterdam's website, but the King of the Netherlands officially inaugurated the operation of the sea lock on Wednesday, the 26th of January. And with a push of a button, King Willem-Alexander opened the interlock door of the world's largest sea lock from the Lock Operations Center. So the picture at the upper left obviously is the sea lock fully constructed with the doorways in the closed position, and then in the larger image to the right, we see King Willem-Alexander announcing the opening of the lock and it's successfully opening. And with that, I would want to acknowledge the folks at Arcadis in the Netherlands and in the US that contributed to the project. And then I'd also like to acknowledge some of the other project partners from whom I lifted some of the photographs that we looked at today as well. So with that, Thad, that would wrap up my presentation for today. I'd be happy to answer questions and appreciate your attention.
Fantastic, John. I think you can see why we wanted to have John present today. Just a plethora of information, high level. You did an excellent job. Very detailed for sure. We would like to open it up we've got a few minutes here before the top of the hour for some questions. So if you have a question, please put it in the chat and Brad will let you know. If not, then we can definitely close it out. So if you have a question, please feel free to throw it in the chat for us.
Dr. Richardson, Tom Gambucci had a question about the braking bars, just more of a explanation on why they were called braking bars and maybe some other detail on those.
Sure. I think I had the same question a day ago when I was putting the talk together. So it's pretty relevant. I was thinking that I think that the name really comes from braking bar from breaking up the flow. So I think I'm not sure if it's standard language or slang that was developed for the project, but the thinking was this, and I think the slide that I've moved to might not be the best one, but if you were imagining these doors, and maybe I'll go to a slide that just shows the doors themselves. If we look at this slide and we look at the image at the upper right, you have these three vertical slats that cut across the opening through which the leveling flows will go. And when the flow is being issued or coming out of one of these openings, with the slats in place, you will create I'll call it a jet flow, but it's really it's the higher speed flow coming out of the opening. And that jet or higher speed flow can persist a certain distance away from, in this case, it's the doorway into the lock. And the idea is that suppose we, to level the locks, just pull the sluice gates all up very quickly. And so with a high head difference, all this water starts to pour through the leveling system. Then these jets or high-speed flows will move into the lock, and if they persist for a certain distance, we'll just say a great distance in this case, then if I have a vessel that's moored in the lock, then that flow will exert a force on the vessel, and in order to keep the vessel in place, I'll need to have a mooring system that's adequate for it. And so one of the things that the lock fill simulations are used to do is to kind of arrive at an optimum gate actuating speed such that the leveling times are acceptable to all, and then the disturbances by the flow in the lock are minimum. And the braking bars are intended to help with that by breaking up the flow coming out of the opening. So with the slats in place like you see here, you've divided kind of one big flow through one opening into 1, 2, 3, 4 smaller jets. Those smaller jets will break up over a shorter distance. And so I think that was a long-winded saying I think breaking bar means break up the flow, which is a kind of an unusual terminology. At least that's how I was thinking about it.
No, thank you very much. And just from a physical perspective, what would a typical head difference be that is from one side to the other there?
Sure. And I will admit that I have no idea, but I have a note on this slide. So with this particular lock, head differences will range between minus 1.75 meters to plus roughly 5 meters. And so I think that what we've got is the plus 5 meters would be if you have a tide and a surge. Typically, you'd have a higher head on the ocean side, lower head on the land side, and then in the reverse, you'd be looking at a slightly lesser head when flow would be going from the landward side to the ocean side. But there's kind of the range of values that were being considered.
Excellent. Thank you very much. That, unless you know of any other questions, I think that's it from the chat.
All right, fantastic. Thank you, Dr. Richardson. Really appreciate your time today, getting on the call. Appreciate everybody participating. We're going to start our next track if you're abruptly at 9:10. So if you have an opportunity and you want to jump on that, please do. But Dr. Richardson, thank you very much. If you guys have further questions, you do have his bio, so you can reach out to him. You can see that he's got a wealth of knowledge. So I know I'll be reaching out at a later date as well. But thanks, and have a great weekend, Dr. Richardson.
Hey, sounds good. Take care, everybody.
Thank you.